the third session of this Victor short course. So just wanted to say thanks for those who submitted their assignment from last week. It's really great. I just looked at a few of them, and you guys managed to get the DM, make a profile, and share that. And some of you were directly using the notebook. Others were using some AI chat to add a couple of lines of codes to the notebook. So that's exactly what we want, and that's really great to see some results from this first assignment and first session. So thanks all. So today I really have the pleasure to have our first guest speaker is Mattia Di Michele Vittori, and he's a researcher from INGV Pisa in Italy, and he's going to talk about a very important part of our short course, which are differential equations, which are equations that we found in many models that we have on Victor, and he's going to show us some ways to actually solve these equations. So we shared a PowerPoint with some slides yesterday with you all. So if you didn't have time to look at these slides, don't worry, but that was a good introduction to what we're going to do today. So make sure you look at the slide as well as going through the notebook that Mattia is going to share today. If you have any questions, comments, put them in the chat. I'm going to be there also to track that. And we also have the Slack channel that can be used as well outside of class hours. So don't hesitate to keep populating these different links with some comments and suggestions or questions. All right, Mattia, yours.
Thank you, Sylvain. Thank you for the invitation. Yeah, so there were a few slides that I shared. This slide will help because in the slides there are some of the equation that we will try to solve with the notebook. So in the notebook, maybe the formatting is not the best. In the slide, we can see how these equations are derived. And there are also in the slides a brief explanation of a method that we will use to solve a nonlinear equation. So let me try to share my screen first. Share.
I just wanted to add that the notebook that Mattia is going to share is available on the folder, on the share folder we have all together. So if you go on the same link as usual on shared education, I think it's spring 2026 short course, and then go into week 3, then you will have the notebook that Mattia is gonna go through.
So please, can you tell me if you can see now my screen, the slide?
Yep.
Okay, great. So differential equations are really important in the modeling of Earth science because they tell us how systems evolve. How systems evolve both in time and space. When we combine both the things, usually we have what are called partial differential equation. Partial means that we have derivative with respect to different variables that can be time and derivative in space. One simpler case is the case of ordinary differential equation, which involve just the derivative with respect of one single variable, like for example, time. In this case, what we see here is a very simple equation, which is Newton's cooling law, that tell us how the temperature, which is denoted here with a capital T, which can be, for example, the temperature of an object, the temperature of a body, but it could be, for example, if we consider a magma chamber as just a point with a uniform temperature, it could be the temperature of the magma chamber that change because we have some exchange of heat with the ambient. And the ambient has a different temperature, which is denoted with TA. And so the temperature of our body will evolve because there is a difference in temperature between our body and the ambient. And so the rate of change in time of temperature is proportional through the constant K is proportional to the difference in temperature. And so this is a really simple equation, which when solved will tell us how the temperature will evolve in time. And it's called ordinary differential equation. As you can see, the derivative is only a derivative with respect to time. Here in the definition, I wrote that there could be one or more derivatives because an ordinary differential equation could involve the first derivative, but also the second derivative. But the important thing is that in an ordinary differential equation, the independent variable is just one, and so we have only derivative with respect to one variable. In this case, we only have derivative with respect to time. These kind of equations are really important in earth science because they model, as we have seen from this equation, cooling or heating of materials. But they can model, for example, the radioactive decay, which is used, for example, for the dating, for example, samples, or in chemical reaction kinetics, or in mass transfer in simple system. I have just one slide on partial differential equation, just to give you an example of and to show what are the difference. So in this example, for example, we have again temperature, and here we have the rate of change of temperature in time is proportional in this case to the second derivative in space of temperature. So this is what is the so-called heat equation. We can imagine in this case that it's an equation that it's modeling, for example, if we have a body, not just the evolution in time of the average temperature, but also the evolution in space of the temperature inside the body. In this case, we have only one derivative in space, so we are imagining, for example, a 1D object. That could be, for example, 1D rock layer between two different layers with different temperatures. And so in this case, this partial differential equation can model a lot of other processes that are important in earth science, like heat diffusion in the earth crust, groundwater flow. But today we will start from, we will look just a simple case, which is the case of ordinary differential equation. So like the one that we have seen before. And in the notebook, we will work with, we will start with one equation, which is the equation for radioactive decay. So we will look here in the slide at how we can derive the evolution equation for the radioactive decay. And then we will try to solve it numerically with a few different methods, trying to understand what are the advantage and disadvantage of different methods that we can use. So the radioactive decay, as I said, is important, for example, for radiometric dating of rocks and minerals. And the main thing is that we start from some isotope, which is the parent isotope that decay over time. And this decay is proportional to the number of isotopes that we have at some time t. So if we partition our time in uniform intervals with delta t, so our grid of times can be called and denoted with an index k, where tk is k multiplying this time step. And now we want to see what happens from one step to the other. So at the new time step, the new number of isotope of atoms will be the old one minus the fraction of the old ones that decayed. So these things that we see is exactly the law that tells us how to update in time the number of atoms that we have. So here you can see that we can collect nk, and so we obtain this equation to update. This can be iterated because we obtain a recursive expression. And so if we go back, we can write the actual number as a function of the initial one. But let's go back to this expression. So as I said, an ordinary differential equation expresses the rate of change. So the change means that we are looking at the difference between the new value and the old value. If from this equation, can you see when I highlight the text here?
Yep.
Okay. So if we want to look at the difference, we can move this term to the left. And by moving this term to the left, we have exactly the difference between the new value and the old value. So we have the change. So we start from this one. We move nk from the right to the left. And then we want the rate of change. So we divide by delta t. So by doing that, and then by taking the limit for delta t that goes to 0, so when we divide by delta t, on the left we will have nk plus 1 minus nk divided delta t. On the right we will have minus alpha divided delta t multiplying nk. So if we take this limit and we define as lambda the limit of alpha divided by delta t, you see that we obtain exactly an ordinary differential equation. This is the ordinary differential equation that we will solve numerically today. So we have derived this equation where, as I said, Nt denotes the number of atoms or the concentration of atoms at the time t. T is the independent variable that evolve, and this lambda will be a constant which is specific to the isotope. So for us, will be a constant parameters that we define at the beginning. What is important is that for this kind of equation, we have also an analytical equation solution. And it's good to have an analytical solution because if we have an analytical solution, we can compare the numerical solution with the analytical one and check if we have more than one numerical methods, which one give the better solution, the best solution. So let's move now to the Python notebook. And we will see now how to implement the numerical scheme. So this is our starting equation. And when we solve numerically the equation, what we have to do usually in a method which is called finite difference, in the finite difference method, we replace derivatives with approximation. And here, in some way, we are moving in the opposite direction with respect to what we have done before. Now we start from the equation, and now we replace the equation with the approximation. So we replace the derivative with this approximation, which is the derivative is approximated with the new value minus the old value divided the time interval. Okay, we can do this thing for this right term, but you see that we have n also on the right. Now we have two choices when we have to solve this. We can use here n computed at the new time step or the old time step. And these give us two different methods. So when we use on the right the old time step, so when we use the values of nk, this is called the explicit Euler method. So we will look at both of the possibility to use here on the right the old time step, obtain it what is called explicit Euler method, or the new time step, which give the implicit Euler method. So let's start from the explicit. So the explicit will replace our original equation with this expression. Now we can multiply all the terms by delta t. Then we can move nk to the right, collect nk, and we obtain the new values as a function of the old one and the time step. And this is exactly what is implemented here in this first Python script. So we import the libraries that we need. So we will use NumPy to define and create arrays in Python. And then we import also matplotlib in order to be able to plot the solution in our notebook. Then we define first all the constant. So the constant lambda for the decay, then the initial numbers of atoms, then the final time and the time step. Then we use the NumPy function aRange, which create a grid, a uniform grid of time values between the initial time, which is 0, and the final time with this time step. So you can see that here we are not using exactly the final time step, but we're using the final time step plus the time step. This is because the function aRange will not add to our array of times the final time. So if we use just t final time, this could stop before the final time. In this way, we are sure that also our final time will be part of the array of times for which we want to compute the solution. So now we have an array of discrete times. And then we use the Python function len to look at the number of time steps that we have created. Now we want to initialize also an array for our discrete solution, which will represent the number of atoms at each time step. So we created this with the NumPy function np_zeros, which initialize an array full of zeros with the same length of the time array. And we initialize the first value, the first element of this array with the initial number of atoms. And now here we do a loop for all the time steps where we update the solution at the new time step based on the solution at the previous time step multiplied by this. And you can check that this is exactly the expression, the formula that we derived before. So we are exactly implementing the Euler explicit method. We iterate, and then at the end, we create a figure. And in this figure, we plot on the x-axis, we will have the values of time. On the y-axis, the number of atoms. So let's run this script. And here we can see that we have the expected exponential decay. So we start from 100, and then at each time step, the number decreases. As I said, the rate of change is proportional to the actual number. So you see that the slope is decreasing and going to 0 when the number of atoms goes to 0. So it seems that this method works, but let's start to look at something. Is this method sensitive, for example, to the time step? What happens if we increase or decrease the time step? And so let's do exactly the same thing. So the only difference is that now we increase the time step. Before it was 1.0, and now 15. So I don't know, can you participate only through the chat, or also if I have some question for you, you can answer?
Oh, everybody's got access to a microphone, so they can answer.
Okay, so before running the simulation with an increased time step, what do you expect that could happen if we increase that? Do you think that it will always work? It will always give this exponential decay, or there could be some problem? Okay.
Probably the number of time steps, it will be sufficient or not to reach the same result.
So there could be some problem, and we can already see what could be the problem by looking also at the good solution, because we have computed a rate of change from the initial value. And this rate of change is what gives the slope of this first part. If we increase the time step, we will continue to move along this slope, but for a longer time. And so you can imagine what happens if you take something which is larger than 15. I don't know if you could see my pointer.
Yep.
But you can see that this could go down and could go below 0. Mm-hmm. So let's try to run this one. And we can see exactly what happened. Mm-hmm. We have the same initial slope, but by using this slope for a time step which is too long, we have a solution which is, well, we see that it's unstable because there are oscillations, but it's not just unstable, because what we are trying to compute is the number of atoms. Is it possible to have a negative number? No, so it's not even a physical solution. So we have seen that this explicit method, it's extremely easy to apply and to implement, but it could be unstable if we take a time step which is too large. So I told you at the beginning that we have two options when we want to solve numerically. One was to here use on the left the values that we already know, because we start from one value, which is nk, and then we want to compute a new value. So this is why it's called explicitly, because the new solution can be written explicitly in terms of the old one. The other possibility is to use here on the right the new value, which is still unknown. But what we can see here is that if we multiply both of the terms by delta t, then we move these terms on the left and we collect nk plus 1. It's possible also to write, so to work on the implicit Euler method in order to find a formula that gives us the new value in terms of the old one. And so here we have exactly the same script. At the beginning, we have the definition of the parameters. You can see that here we have 15 as time step. So the time step that was giving us problem and an instability with the explicit method. Then we create the array of the time steps. We compute the number of time steps. We initialize the array for the solution. We initialize the first element with the initial value, which is the same as before, 100. And then here we use the formula that we have obtained for the implicit scheme. So it's the old one divided 1 plus lambda multiplying delta t. We created the figure, we plot our solution. And what you see is that we have obtained now a solution that at least physically is more reasonable than the previous one. So we have already seen an advantage of an implicit method with respect to an explicit method. This implicit method, so the implicit Euler method, is unconditionally stable. What does it mean unconditionally? It means that the condition of stability is not related to the time step, while the explicit method is called conditionally stable because there are some conditions on the time step for which the method will be stable or not. And we have seen that with delta t equal 1, we had a stable solution. With delta t equal 15, the method becomes unstable. But the stability is not the only thing that we are interested in, because a method could be stable but give the wrong solution. So whenever you want to solve numerically an equation, a partial differential equation, an ordered differential equation, you have also to look at something else, which is called the scheme accuracy. That means how close the numerical solution is to the true exact solution. So we have to compare the numerical solution with the analytical solution. And as I said before, there is one good thing for this simple example, and it's that we know what is the analytical solution. So by knowing what is the analytical solution, we can do a comparison between the numerical solution that we computed and the analytical one. And so let's look at this new script. Again, we initialize all the parameters. We create the array of the time steps. We compute the number of time steps. And then we can use here the numpy exponential function applied to the array of the time steps in order to define the analytical solution at all the discrete times of our array. So here we have exactly computed what is written here. So it's initial number multiplying e raised to the minus lambda t. For the numerical solution, we do exactly what we have done before. We initialize an array with the same length of the time steps. We initialize the first element of the array, which is so the number of atoms at the time 0 with the parameters that we defined here. And then we do the loop, the iteration, to update with the explicit scheme the numerical solution. We create a figure, and now in the figure, we plot both the analytical solution and the numerical solution computed with the explicit scheme. And here we can see what are the plot. We can see that there are some differences that are larger here and then they decrease. So usually we are interested in what is called the error. So we don't want just to plot the two solutions, but it's interesting also to plot the difference, so the absolute values of the difference between analytical and numerical solution. And so this is what we do in the next script, where we plot the absolute value of the difference between analytical and numerical solution computed with the explicit scheme. So we can see exactly what we have seen before, so that the difference was 0 at the beginning because we initialized both the solution with the initial value. Then it increases with time, and then it becomes smaller. So we can see this plot. Sometimes also plotting the absolute error is not the best thing, because the absolute error gives us an idea of the magnitude, but it's not the same to say that there is an error of 1, for example, when the correct value is 10 or when the correct value is 0.1, because they represent relative error that are different by order of magnitudes. So let's plot what is called the relative error. Oops, sorry. Which is given by the absolute value of the difference divided by the real solution. You can see here that we are not just dividing by the real solution, but we are adding this epsilon, which is a very small quantity. Why we are doing that? Because otherwise, if we compute the relative error by using the analytical solution, when the analytical solution goes to 0, here we are dividing by something that goes to 0. And so this could create a problem, round-off problem, or numerical errors, because we are doing maybe a division by a number which is too small. So we add a small quantity in order to avoid division by 0. So let's plot this. And here we can see now that the relative error is increasing, starting from 0 to 0.5. 0.5 is the relative error. It means that we have an error of about 50% in the solution at time 10 seconds. Let's go back now. If we decrease the time step to 0.1, what do you expect to see here in the relative error? To remain the same, to decrease? Any idea? To decrease. And do you have also an idea of how much it should decrease if we move from 0.5 by 0.1? So we are decreasing the time step by a factor 5. And so let's see. So we compute the new. Well, we already see that now the numerical and analytical solution are really close one to each other. The absolute error, now I don't remember here what was the value of the absolute error. Now let's see. And now you see that it was 0.5 something, now it's 0.12. So more or less the relative error decreased by a factor 5. So we decreased the time step by a factor 5, and the error, so the cumulative error also decreased by a factor 5. And this is because the approximation that we used here for the derivative is what is called the first order approximation. First order approximation means that the error is proportional to the time step. So if we decrease, is proportional in a linear way to the time step. If we decrease the time step by a factor 5, also the error will decrease by a factor 5. Today we will see only first order scheme like this, but if you use approximation of the derivative, like for example Runge-Kutta method that can be of higher order, second, third, or fourth order, this means that the error in the approximation of the derivative will decrease not proportional to delta t, but proportional to, if you have a second order method, proportional to delta t squared. So if you decrease delta t by a factor 2, the error will decrease by a factor 4. If you use a Runge-Kutta of the fourth order, it means that if you reduce delta t by a factor 2, the error will decrease by a factor 2 raised to the fourth power, so by a factor 16. So this is another important thing, that when you approximate some derivative, it's important also to know the order of the derivative in order to understand how much the error will decrease when you decrease the time step or the space discretization step if you are integrating in space instead of time. So also in this case, one could think, okay, so it's always better to use higher order scheme. That it's not always true, because some scheme of higher order could become unstable in some condition.
Yeah, there's some questions in the chat, Matthias. So one is,
yes.
This epsilon value that you mentioned that, you add in order to avoid dividing by 0. You just put a small number there. The question is there an interval to define the epsilon value? But I guess as long as you put a very small number, you're fine, right?
Yes.
Okay. And then
so usually you want to multiply to add something when you have a division in a script or code. Whenever you divide by something and this something is a variable of your code, it's always good to add something, and this something should be a small quantity, small of the order of the precision of the machine. So, for example, if you are writing a code in single precision, it should be the small quantity related to the single precision. If you are writing a code in double precision, it should be something related to the double precision. And usually, the languages have some specific function that give you this epsilon. So in Fortran, I think it's really called epsilon. In C++, I don't remember, but I'm sure that also in Python, there is a function that will give you this small quantity, which corresponds to the machine precision, that then you can add to the denominator in order to avoid division by 0.
Okay, right. There's another question. How much does the computing process is affected by the decrease in the size of the time step, and how to justify the size of the time step in order to reduce your error while avoiding a bias?
Okay, so also this, the answer to this question is related to the order of accuracy of the derivative. Because if you have a first order method, so when you decrease the time step by a factor 2, you increase the number of time step of a factor 2, because you want to cover the same time range. If you have a scheme of order 2, and you want, let's say something, that you want to decrease the error by 1 order of magnitude. With first order scheme, you have to decrease the time step, and so increase the computational time by a certain amount. If you have a second order scheme, you need you have to decrease the time step, but less with respect to a first order scheme. So an advantage of higher order scheme is that in order to decrease the error, you need to increase less the computational time, let's say.
Yep, makes sense. Yep. Thanks. That's all for now.
Okay. Now, we have seen so a couple of things: stability and accuracy. We have seen that the implicit scheme is more stable because the stability does not depend on the time step. And then we have seen the accuracy for the explicit time scheme. We could repeat exactly the same thing here, and let's see, for example, if we do the accuracy analysis for the implicit time scheme instead of the explicit, let's see what we have. So the implicit formula is this one. So I will copy this update formula to this. So let me, so I will still call it explicit, but we are using the update formula for the implicit. And so let's see. Oh, some error. Oh, yes, because it's also DT. Here it's called DT comp, and lambda is called lambda coef. What is the error? Explicit comp. Okay. So let's look here at the. Okay, now I have updated. So here I used the formula for the implicit, and you can see that the relative error is exactly the same. So explicit or implicit have the same accuracy, and this is because the accuracy is not really related to the fact that here we have used the new or old values. The accuracy is mostly related to the approximation that we use here on the left for the derivative. So if the accuracy is the same and implicit is more stable, the question is why using the explicit? Maybe it's if implicit is always better, we could always use the implicit scheme. So let's try to understand why sometimes we have to use the explicit scheme. And we will understand that by looking at another ordinary differential equation. In this case, we look at an equation that tries to model the volumetric water content in a layer of soil as it decreases to percolation. So the variable theta express the fraction of water, so the volumetric fraction of water in a layer of soil, and this decrease, and the decrease depends on the hydraulic conductivity. So the larger is the conductivity, the larger will be the variation of water. So we are losing more water, the higher is the conductivity. And the conductivity here is given as a coefficient, so what is called the saturated conductivity, multiplying the actual water content, but in this case raised to some exponent. So it's not linearly proportional to the water content, but it's proportional to this theta raised to the n. So what is the problem here? Let's continue with our notebook. So this is our equation. So let's try to do again to apply the explicit scheme, and then we will see that when we want to apply the implicit scheme, it's not as simple as before. So for the explicit scheme, we will do exactly as we have done before. We approximate what we have here on the left with new value minus old values divided delta t. And then here for theta, we use the previous value when we want to use the explicit scheme. So new script, we import the parameter, the libraries that we need, NumPy and matplotlib. We define here the parameters of the simulation. So we define the hydraulic conductivity, so these parameters Ks. We initialize the exponent. In this case, the exponent is 3. We define here the time step, the maximum time, the initial value for the water content. And we do exactly as we have done before. We initialize the array for the discrete times. We initialize the array for the explicit solution. We assign the values for the index 0 of the array, which is the initial value of the solution. And then we update with the explicit scheme of the solution. So the value of the solution at the new time step is the value of the solution, this theta prev, which is the values at the previous time step, minus dt time step multiplying the coefficient, multiplying the value of theta at the previous time step raised to exponent m. We run this script and we obtain this solution. With this time step is stable. We know that if we increase the time step, I don't know, an order of magnitude, let's see, it's still stable. If we increase more, okay, in this case, it's still stable, but we can imagine that if we increase too much, then it will become unstable because this could go below 0. So let's go back to the previous one. And now let's try to implement the implicit scheme. So the implicit scheme means that we discretize here again this derivative as new value minus old values divided delta t. But here on the left, we will take the new values of theta. So this means that if we move everything, so we multiply by delta t and we move everything to the left, we will have old value, sorry, new value minus old values, and then we have delta t, ks, and here we have the new values raised to the power m. The problem is that this is a non-linear equation in the unknown theta k plus 1. We cannot do as we have done before. So in the previous case, if you remember, we could collect the terms and then write the new values in this way. Now we have a non-linear equation, and so we cannot write explicitly the new value, which is theta at the time k plus 1, as a function of the old value. So the difficulty in the implementation of implicit scheme is that if the ordinary differential equation has some non-linearity, like here we have a non-linear term, then to update the solution we need to solve a non-linear equation. So we need to find here what is the values of theta k plus 1, which is a solution of this equation, where delta t, ks, and theta at the previous time step are known. So if theta at the new time step is denoted with x, our problem is to find the values of x for which this is equal to 0. So we need to find a solution of a nonlinear equation. This can be done numerically, but for sure it's more computationally expensive than the simple explicit scheme. And let's see how we can find a solution of a nonlinear equation. So this can be done with the so-called, for example, there are a lot of methods, but one of the simplest is to use the bisection method. So let's imagine that we have a function, which is this black line. We want to find where this function is equal to 0. So we want to find the intersection between this and the condition y equals 0, so the x-axis. If this function is continuous, and we know that on one side is negative and the other is positive, where somewhere this should intersect the y equals 0 line. So what is the idea of the bisection method? To start with an interval for which we know that on the left the function is negative and on the right is positive, or the opposite. It could be positive on the left and negative on the right. Then we take the middle point and we look in the middle point if the function is negative or positive. If it's negative, then we can restrict now our search to the right half of this interval. So we know that in this point M1 the function is negative, in B is positive. And so we can iterate again and look at the middle point, which is M2. In M2 we evaluate the function and is positive. So we know that now in M1 is negative and in M2 is positive. And so we can iterate, divide every time by 2 the sides of the interval where we are searching, until this interval is small enough, or until the values of the function in the middle point is close enough to 0. So this is what is called the bisection method, and the steps are: first, to find 2 points where on one side the function is positive and the other is negative. So it means that the product has to be negative. Then we compute the midpoint. If in the midpoint we have that the values of the function is close to 0, then we have already found our solution. If it's not 0, then we check if the product of the function in one of the extreme and in the middle point is negative. If it's negative, it means that AC will be the new interval. Otherwise, it will be CB. And then we repeat with the new interval. And this is exactly what is done here in this script. So in this script, we try to find, for example, a root for a function. Here we have a quadratic function. So it's a parabolic function. We define a function for which we want to find the 0. We define first the edges, the limits of the interval, in this case minus 0.5 and 1.5. We define a tolerance. This tolerance is to check that when the value of the function is smaller than this, we consider our point a good solution, close to being a 0. And then also we repeat this iteration of dividing in intervals here a maximum of 20 times. Maximum of 20 times means that we started from an interval with width 2, from minus 0.5 and 1.5. At the first iteration, we divide by a factor 2. So it becomes 1. Then at the second iteration, 1/2, then 1/4, and so on. So 20 iteration, you can see that will give you a very small interval. So we will give you the solution with a good approximation. And now here we are doing exactly what was written in the slide. We compute the function first in A, then in B. Then we check, first of all, that the product, so this condition, that only if on one side is negative and the other is positive, we can apply this algorithm. So if the product is greater than 0, then we have a problem because we cannot find the root, the 0 there. Otherwise, we proceed. We initialize with these two values. We initialize to 0 the counter. And then we create an array where we want to store the location of the midpoints. Then we write here on screen for each iteration, A, B, the middle point, the value of the solution at the middle point, and the width of the interval. And then we are just applying this iteration. So we increase the counter, we take the middle point, we compute the function in the middle point, we append this value to the array of midpoints, we update the interval of the width, and then here we are just writing on screen what we are doing, and then here we have our algorithm. If the function computed on the left of the interval multiplying the value of the function in the middle point is smaller than 0, then it means that we have to update our right edge of the interval with the middle point. Otherwise, we have to update the left edge of the interval with the middle point. And so we can see here what we have done. We have started with these two black points. Then M1 was the first middle point. So the new interval is between 0.5 and 1.5. The new middle point is M2, and M2 in this case, it's already the exact solution. And so after 2 iterations, the algorithm converged to the solution. So let's try to change a little bit, for example, these. So if we write 3.1, okay, you see that by changing the solution, then we had here going to 0.5, 1, so it took more iteration to converge to the actual solution. Or let's try. I don't know if here we have. So here, okay, it took 11 iterations, and you see that, in this case, it was not converging because the first 2 points, A and B, were both with positive values. So we were in this case, and so the algorithm could not converge. Okay, so let's go back to the original one. But what we have seen is that when we start from values for which the values of the function is positive and another one for which is negative, this algorithm will always converge to a 0. So this is a way to solve a nonlinear function, and this is something that we can use to solve the nonlinear function that we obtained with the implicit method for our ordinary differential equation. So we can combine now the bisection method with this scheme. So that means that at each time step, we obtain an equation of this form. We will use the bisection method to find the new value, and we will iterate in order to obtain the solution with the implicit method. So we have to define here this function, which is exactly the function that we need to solve. So it's this one. So this function, if we look, it's our unknown plus delta t multiplying the coefficient plus the unknown raised to the m minus the old value. And so let's look at what we have here. We have the values at which we are computing the function, plus this term, which is delta t multiplying the coefficient, multiplying x raised to the m, minus the previous value. So this function computes exactly what we have here. So we have the function that we have to iterate in the bisection method in order to find the solution. And so here we are doing exactly this thing. We create our parameters. We define the tolerance and the maximum number iteration for the bisection method. We create the array for the times, the array for the implicit solution. We initialize the implicit solution. And then we have now at each time step to do what we have done in the previous script. So we have to use the bisection method in order to find the solution of this equation, which will allow us to find the new solution, implicit solution. So let's run this script. And here we have found the implicit solution. So what is the message here? That we have seen two different methods for the solution of ordinary differential equation. Explicit, which is extremely simple even when the right-hand side is nonlinear, and then the implicit. We know that the implicit is unconditionally stable. We know that implicit, explicit have the same accuracy. But the problem with implicit scheme is that this requires, when the terms on the right is nonlinear, to solve a nonlinear equation, which could be not always simple. So we have seen one method, which is the bisection method, to solve this nonlinear problem. But in general, and also when you have more than one equation, so in this case, you will have to solve not just a nonlinear equation, but a system of nonlinear equation, which becomes also even more difficult. So it's more common in numerical codes to use explicit methods, like we have done here. And what we have to take care is that we have to take care of the time step, because most of the time explicit methods are conditionally stable. So we have to look at the conditions that make our explicit scheme stable. So work on the time step in order to look to have both the accuracy that we want and also to be sure that the scheme will be stable. In this, so I will stop here. In this notebook, you will find also some exercise which are still related to this thing. So I suggest you also to try to do this exercise where we are trying to put together the things that we have seen today also in different ways and for different problems.
Great, thanks, Mattia. So just have a question for you about the adaptive time steps. So we know that in some models you can actually adapt the time steps. So then it's going to check the value of the previous value and then the next value. And if the difference is too high, you can like reduce that time step and then or increase it again.
Yes.
Can you talk about that?
So there are a few ways to look at to create an adaptive time step. Not just by looking at the difference with the previous time step, but for example, you could advance with one full time step or advance with 2 half time steps, and look at the difference that you have in this way. Or you can use, for example, there are methods that are called Runge-Kutta 4-5. These Runge-Kutta 4-5 methods are used because you can evaluate both the new solution with the 4th and 5th order schemes, and then you can compare the difference in the solution that you obtain by advancing with the 4th order and 5th order. The difference that you obtain will give you an idea of the accuracy, and based on the error, then you can reduce or increase the time step.
Great. Yeah, we actually have a notebook about that that Chuck Connor made a couple of years ago. So we can share that with everybody as well to see the difference. In the
so one suggestion, yes, one way could be, yes, also these that I was mentioned. It would be really easy, for example, to modify one of the scripts that we have seen for an explicit scheme by computing exactly the full time step or 2 half time steps. Look at the difference, the relative difference, for example, and based on the relative difference, you can increase or decrease the time step for the integration.
Yeah, that would be a great exercise to do. Great. All right. We're running out of time, but again, you guys can use the Slack channel, emails, everything we have in place for suggestion, comments, questions to Mattia and what we did today. And so I think the assignment would be to look at the exercises and try to change some of the parameters in there. There's no formal assignment, but if you guys can do that this week until next week, and then put any questions or comments you have in the Slack channel, that would be great. Thanks, Mattia.
Yes, one thing that you can also try to do is to plot in the same plot for the first exercise that we have done, to plot the analytical, implicit, and explicit solution. Because you will see here, by doing that, that one systematically overestimate the real solution and one systematically underestimate the numerical solution. So you can maybe think a little bit about why this happens, if it could be always like that, or if it's due to the shape of the analytical solution. But also it's important not just to see the accuracy, but also if this is over or underestimate of the correct solution.
Yep, that's good. Yeah, great. All right, thanks, Mattia. Thanks, everybody.
You're welcome.
And see you all next week.
And thank you, everyone, for attending this.
Thanks. Bye.